I am back because I want to do more calculations. So I'll begin by sharing my screen, and I'm going to do sequences because I love sequences. So although for someone who claims to love sequences, I actually have forgotten quite a few formulas about them. Let's see if I can independently discover them or convince myself of their discovery. And let's just get straight into it. No better way to do things, right? Just dive straight in. Find the next three terms in each sequence. Okay, so we see it's going plus, minus, plus, minus. And we see it's going up in powers of 3. So the next three powers of 3 are 243, 729, 2187. And there would be a minus sign there. That one would be positive, and there would be a minus sign there. Like that. What's really happening here is we're multiplying by -3 for each successive term. Next up, we're just clearly adding 100 each time. So it's going to go 509, 609, 709. And here we go 0, 3, 8, 15, 24. Well, this is one less than each square number. A sequence of square numbers, which you should know up to the 20th square at least, goes 1, 4, 9, 16, 25. And therefore, who will be next? The answer is 35, 48, 63. Now here, it goes half, half, 3/8, 1/4, 5/32. What a strange sequence, right? We could look at the gap, the absolute difference between each term. So we'll do that just to start off with. 0. And what's a half take 3/8? Well, that's 4/8 take 3/8. So that's 1/8. So we're going 1/8 down. That's 2/8. So we're taking away an eighth again. And then here, goodness me, what on earth is this? Okay, so 16/32 take 8/32 take 5/32. Well, that's 3/32. Not too sure what's going on here. I'll make everything have a common denominator of 32. How about that? And see if I notice something. Okay, so it would go 16, 16, 12, 8, and 5. Still not sure what's going on in this sequence. How unusual is this? How unusual. How about multiplication? Times by 1. Times by what to get that? 16/32 times by something equals 12/32. Well, 16/32 divided by 12/32 will give me the answer. So that's 16/12, which is 4/3. Did I do that right? I am doing this right, aren't I? Oh, goodness me. No, I'm completely messing this up. I guess I'm a little bit tired. Perhaps I shouldn't be doing this. But I'll just push on. It really doesn't matter. Okay, so yes, it would be C divided by A equals B. Whew, goodness me. This is the effect of tiredness. 12 over 32 divided by 16 over 32. That's better. So now it's 12 over 16, which is 3 over 4. Oh, I think I've cracked it. So that's 3/4. Next. It will be 8 over 12, which is 2 over 3. And then it will be, what, 5 over 8? So what's that? 1, 3, 2. I have no idea. I have absolutely no idea what's going on in this sequence. We'll come back to it. We'll come back to it. That's something you should be able to do. Come back to something. Okay, next one. Oh, these are the even squares. 2 squared, 4 squared, 6 squared, 8 squared, 10 squared. So next comes 12 squared, 14 squared, and 16 squared. Gotcha. This, I'm just adding on 20 each time. So 114, 134, 154. And here, well, this is secretly 5 over 1. So next it would be 5 over 32, 5 over 64, 5 over 128. It's going up in powers of 2 in the denominator. And then here we've got the minus plus minus plus pattern. So we're going to have a positive, a negative, and a positive. And what's the actual pattern though? Well, the negative numbers appear to be 1 9, 3 9, 5 nines. So I'm going to say 7 nines. Like that. And the positive numbers appear to be like 1 on both ends and zeros in the middle. But how many zeros? 1 0 3 0. I'm going to say 5 zeros. And then 7 zeros, yes. There's probably a more sophisticated way to describe that doesn't rely on the pattern digits, but it doesn't really matter. Okay, the 10th term of each sequence. So for the first one, we notice that we go from -1 to 2/3. So that is like adding on 5/3, and then that holds true for the next one and the next one after that. So it's adding on 5/3 each time. So the way that I was taught to do this was to find out the secret 0 term, the 0th term, if you like. So if I'm adding on 5/3 each time, that's my common difference. What I'm going to do is I'm going to take away 5/3, which takes me down to -2 and 2/3. And then I'm going to add on 5/3, but multiply that by 10. Multiply that by 10 to get the 10th term in the sequence. Okay, so -2 and 2/3 is -8/3. 5 thirds times 10 is 50 thirds. You put these together and you get 42 over 3, which is 14. It's 14. Next, we have 7, 9, 12, 16, 21. No idea. So let's see. Gap of 2, gap of 3, gap 4, gap 5. I understand. You know, in this case, it would actually just be quicker just to count up and make sure that you do it right, of course. So 5, so add on 6 and we get to 27. Add on 7 and we get to 34. Add on 8 and we get to 42. Add on 9 and we get to 51. Add on 10 and we get to 61. Just there like that. Fine. Here we are multiplying by -3 each time. By -3 each time. So here's another way to do it. Instead of beginning with the zeroth term, like, do the process that you need to get from one term to the next. But instead of doing it 10 times to get the 10th term, do it 9 times upon the first term. And that has the, like, think of being on the first stair on a flight of stairs, and they say, go to step 10. You're going to be like, okay, I need to just go up by 9 steps. Okay, so -2. And we're going to multiply that by 3 to the 9. Now, what's 3 to the 9? 3, 9, 27, 81, 243, 729, 2,187, 6,561, 19,683. So it's -2 times 19,683. And we do that and we get -39,366. Just there like that. In this sequence, we appear to be going down by 5 each time. So if you're feeling a little bit lazy, you could just go down by 5 yourself. So did I say going down by 5? I guess in the magnitude we are going down by 5, but clearly we're adding 5 each time. So 2, 7, 12, 17, 22 is the answer. And for here, what's going on? Well, it's alternating in plus and minus signs. But how do we get from one term to the next? Well, we seem to be timesing by 3 each time. So it's a times by 3 thing again. So I'll just do what I did up here. I'll multiply -4 by what? 3 to the 9? Multiply it by -3 to the 9, in fact. And an odd power of a negative number is a negative itself. So it will be -4 times -19,683, which is, well, it's going to be positive. So what? 76, 784, 784, 7872, 78732. I think. Something like that. For this 14th one, what's going on? I have no idea. Add on 4, then 2, then 1, then a half. Oh, I understand. Okay. Right. But how to get the 10th term? You know, like before, instead of trying to think about maybe a clever way to do it, maybe it's just best to do the actual computation, you know? So 3 over 2, add a quarter. So that's like 1.5 add 0.25. So 1.75 or 1 3/4 if you like. Next, we have to add an eighth. What's 3/4 add an eighth? Well, that would be 6/8 is 1/8. So 1 7/8. So that's fine. Then add a 16th. So that's 14 over 16. At 16th is 15 over 16. Like that. Then add 1 over 32. So that would be 31 over 32. And last, 63 over 64. I think so. But if you need it as a top heavy, it's going to be 127 over 64. Right. And who's next? 72, 72, 72. Well, it appears to be adding on 200 each time. So, you know, like that. I mean, you're just adding on 1,000, of course, because it's 5 terms up from the 5th. So who's next? 37, 46, 55, 64, 73. And that appears to be going down on the units and up by 1 on the tens. So, gosh, what an elaborate way of just saying add 9. So I just have to add 45 to this. So that would be like 118. Now we have rules for generating each sequence. This here, this tiny little subscript here, like, how does this even work? Well, if I want the first term of the sequence, I just plug in 1, because the first term of just a generic general sequence, we call that A with a little tiny 1 down there. That's the first term of just any sequence that you can think of. The second term is A2, this third term is A3, this fourth term is A4, and so on. So to get the first term of this sequence, in other words, A1, I just need to stick 1 in there. So if I do that, it'll be 2 add 1, so that's 3, and 3 divided by 1 cubed, which is 3. To get the second term, just stick in 2. So 5 over 8. And the third term, stick in 3. So 7 over 27. And the fourth term, stick in 4. So 9 over 64. Here we have the powers of 3, but 1 deducted in the power. So we begin with the 0th power of 3. So it's going to just go 13927. Simple. Here we have the square numbers incremented by a 1. So instead of being 1, 4, 9, 16, it'll be 2, 5, 10, 17. N cubed over 2n add 1, huh? I'll stick in 1, and I'll get 1 over. In fact, it's actually just a reciprocal of these. So 1/3, 8 over 5, 27 over 7, and 64 over 9. Wonderful. To find the 10th term of each sequence, just substitute in 10 into the generation rule. So A10 will just be 21 over 10 cubed, which is 21 over 1,000, which, if you like, is 0.021. A10 will be 4 to the power of 9. which is 2 to the power of 18, which is 262,144. And the reason why I know that is because I know the powers of 2 up to the 30th, I think. Something like that. Okay, so what's the 10th term here? Just stick in 10. So 2 times 10, that's 20. And then 20 squared is 400. Stick in 10 here. So 19 squared is 361. You can see why I like these. The first 4 terms in each sequence. What's going on here? We have 2 pieces of information. This appears to be a kind of recurrence relation. A recurrence relation? What's that? Well, it's like I give you the seed number at the start. So maybe the seed number is like 5. And then the rule to get from one term to the next is, the previous term, just add 3 to it. Oh, I get it. So this sequence is going to go 5, 8, 11, 14. Yeah, exactly. But wait, don't we already have a word for this? This is called an arithmetic sequence or a linear sequence. Yeah, but recurrence relations define more difficult things. Probably the most famous example is the Fibonacci sequence. That begins with 1, 1. So I have to give you 2 seeds to start that off. And the rule for making the next term in the Fibonacci sequence is to add the previous 2 terms. So 1 and 1 makes 2. Then 1 and 2 makes 3. Then 2 and 3 makes 5. Then 3 and 5 makes 8. And so on. The Fibonacci numbers. But for this one here, it begins with 29. And what you have to do is you have to add 20, you have to add 10 each time. So it's going to go 29, 39, 49, 59, just like that. And for this one here, you begin with -1 and you have to multiply by 2 each time. So it's going to go -1, -2, -4, -8, just like that. And here is a kind of a more exotic rule. The only way to see what it looks like is to just run the rules. So it starts with -4. And to help yourself, you can put A1 over there, A2 over there, A3 there, and A4 there, and that's fine. Now, how to get A2? We have to the previous term here, you have to add 2. So -4 add 2 is -2. How to get A3? To the previous term here, right here, you have to add 3. So to that, we say 1. And how to get A4? To the previous term, which is right here, you have to add 4, which gives us 5. What an interesting sequence. We add 2, then 3, then 4. So it's really just going to be the triangle numbers, but shifted down a little bit. And it's unsurprising because that's sort of like the rule for how you generate the next triangle number in the first place. Okay, here, start with 10. That's A1. What about A2? Well, A2 is going to be 2 add 10, which is 12, divided by 2. So 12 divided by 2 is 6. What about A3? That's going to be 2 add 6, which is 8. And 8 divided by 2 is 4. What about A4? That's going to be 2 add 4, which is 6. And 6 divided by 2 is 3. Wonderful. Finding the 10th term in each sequence. And their recurrence relations, are they kidding? Apparently not. So we just have to march on ahead and see if we can find out something when we generate the first few terms. So term 1 is -1. Term 2 is 2 times -1, so -2. Term 3 is 3 times -2, so -6. Term 4 is 4 times -6, so -24. And indeed, we spot that these are the negatives of the factorial numbers. The factorial numbers, as a brief reminder here, we have 1 factorial, 2 factorial, 3 factorial, 4 factorial. And the way that computer scientists say this is 1 bang, 2 bang, 3 bang, 4 bang. That's what I've heard anyway. And it's simply 1 times 2, 1 times 2 times 3, and then, as you can guess, 1 times 2 times 3 times 4. And these evaluate to 1, 2, 6, 24. What is 5 factorial? It corresponds to the number of ways you could rearrange 5 books on a bookshelf. Call the 5 books A, B, C, D, E, and 5 factorial is 120. And so there are 120 ways to shuffle those 5 books. That's how you can think of that. So anyway, so I would need the 10th factorial. How do I get that? Well, let's see. Can I remember? 1, 2, 6, 24, 120, 720, 5,040, 40,320, 362,880, 3,628,800 with a negative sign in front. But if you're stuck, you can use your calculator. Where's mine? Oh, here it is. I think I have a camera good enough that you can actually see it. So this is a standard scientific calculator. So you just type in 10, and it should be on the top, the display. And then you hold down. Wait, where actually is it? It used to be at the bottom. Oh, I spot it. Look for X with a little exclamation mark next to it. So I type in that, and there. I've got the 10 factorial on the display. I press equals, and there it is, 3,628,800. Turn it off. Put it to one side in case I need it again. And there you go. What's going on in problem 30? Begins with 11. Let's make some room. Begins with 11, and then we have to, what? Add on 10 to the previous number. So 21, 31, 41. Oh, it's just a linear sequence. This one's quite easy. It's clearly just the 10 times tables, but just add 1. So what's the 10th term? 101. That should be right. I think so. We'll see. In problem 31, we begin with -3, and we have to multiply the previous term by 3. So this is going to be like -9, -27, -81. Oh, I get it. It's just the powers of 3, but negative. So what is the 10th power of 3? That is 59,049. And then just stick a minus sign in front. Problem 32 involves this with a fraction. So we're going to put negative 14 first and just see what it looks like. So 2 take 14 is negative 12, and negative 12 divided by 2. Now, I'm tempted to put negative 6 here, but do you know what I'm going to do? I'm actually going to put it as a fraction. And then also the actual reality down here. Okay, what's the next one? Okay, so 2 take 6, that's a negative 4, and negative 4 over 2 is negative 2. Gotcha. And then 2 take 2 all over 2 is 0. What is this sequence? All right, 2 add 0 over 2, 1. 2 add 1 over 2, 3 over 2. Oh, is this from earlier? I think it is. Is it? I don't know. We're up to term 6 now, so we may as well march on ahead. So 2 add 3 over 2 is going to be, well, I know it's 3.5, which is 7 over 2, which then divided by 2 is going to be 7 over 4. Term 8 is going to be 2 add 7 over 4, which is 3 3/4. 3 3/4 is 15 over 4. 15 over 4 over 2 is 15 over 8. Right, so we have term 8. And now let's get term 9 and then term 10. 2 add 15 over 8 is 31 over 8, which is 31 over 16. Oh, I can already see it. Do you see it yourself? 1, 3, 7, 15. Those are the powers of 2, but take away 1. So the next one comes simple now. It's just going to be 63 over 32. Great. Probably could have gotten that in a much more sophisticated and better way, but it's a process. So write the explicit formula for each sequence. What do they mean by that? They mean give me the sequence which lets me, give me the rule which enables me to jump to term 1000 with just a few calculations. You know, I don't want to have to calculate all the terms, all the 999 previous terms. I want to be able to just jump to term 1000. So the rule for this one is that you are adding 3 each and every single time. So, you know, that the generation rule for that is just like 3n. Oh, so you're saying it's just the 3 times tables? Well, no, it isn't. It clearly isn't just the 3 times tables. It's the 3 times tables, but shifted down by 15. So we're going to write 3n take 15. Next, we have 6, negative 3, negative 2, negative 3 over 2, negative 6 over 5. What's going on? Add 3, add 1, add a half. So that's like negative 1.5, and that's like negative 1.2. So what? 3 over 10? 3 over 10? Yeah, I don't really get this. I really don't. I genuinely don't. What's actually going on? Well, the difference is getting smaller each and every single time. We look at the common ratio, so we're doing -6 over -3. So that's going to give 2. Beg your pardon. -3 over -6. That will give a half. That will give 2/3. And -3 over 2 over -2. That will give 3 over 4. Oh, I get it. I think so anyway. 6 over 5 divided by 3 over 2. $12 over 15, which is 4 over 5. What a crazy sequence. So I'm multiplying by that every single time to get from one step to the next. All right. Okay, so after like n steps, I know that it's going to be n factorial over n add 1 factorial, but I'm just figuring out how to actually work this through. Okay, so instead of sort of fiddling around with the indices, I just kind of like stick something in and just see if it works. So, oh no. Right, okay. Zero factorial is just nothing. Sorry, 0 factorial is 1. So 1 over 1. I think this works. There's your nth term. -6 multiplied by n factorial over n add 1 factorial. Let's see. So to get my second term, I'll stick in 2. So I get 2 over 6. Two over 6 is 1/3. So -6 times a third. Oh no, it's off by 1. That's how you get the third term. I stuck in 2, and I actually got the third term. So what? Ugh. It's annoying. The tiredness is sort of kicking in. All I have to do is just shift it by 1. So why can't I do it, for goodness sake? Okay. There. Okay, now if I stick in 2, I'm going to get 6 over 24, which is a quarter. -6 over 4. So -3 over 2. So if I stuck in 2 and now I got the fourth term, oh, clearly now it's just -1. I'm doing it the wrong way. There. Can you believe it? Tiredness has that effect. Anyway, recursive formula for each sequence. 2, 4, 7, 11, 16. The gap is 2, 3, 4, 5. And the initial term is 1. Is 2. So un add 1 is equal to the prior term but I want the second term, and so I have to add on. Isn't it just simply this? Oh, so to get the first term, wrong. No, to get term, if I stick in 1, then that just says 2 add 1. That is wrong. Okay, how about that? Try it out. To get the first term, or to get term number 2 rather, that would be term number 1 plus 2, which is correct. So that's fine. Here, we are adding on 200 each and every single time. And the very first term is 15. So the rule to get from one term to the next is to just like add on 200 to the previous term. Okay, that's fine. I really want to know what's actually going on with this bizarre sequence up here. What was it? Oh yes, problem 4. 1 over 2, 1 over 2, 3 over 8, 1 over 4, 5 over 32. Oh my goodness me. Can you see that? N over 2 to the n? Oh man. I should have tried that. No matter. You got to be honest about when you got stuck. And just move on. Okay, so next up, geometric sequences. Guess I should just make sure that the screen is fine. Oh, it is. Okay. Fine. But before that, I'll have a sip of water. So they say, determine if the sequence is geometric, and if it is, find the common ratio. Challenge accepted. Okay, in the first one, we are to multiply by -6 each and every single time, and therefore it is geometric, and the common ratio is -6. In the second one, I don't believe it's geometric. This one, these are the even square numbers, which is not geometric. It's quadratic. It's 2n all squared. This one here, multiply by 5 each time. So the common ratio is 5. R equals 5. -2, -4, -8, -16. Well, the common ratio is clearly 2. I'm doubling each time. And here the common ratio is clearly -5. Given the explicit formula for a geometric sequence, find the first 5 terms and then the 8th term. Okay, so this is the powers of 3, but shifted down by 1. So, the very first term is going to be 3 to the 0, and anything to the power of 0 is just simply 1. So the first 5 terms are 1, 3, 9, 27, 81. And the 8th term is going to be 3 to the power of 7, which is 2,187. Hey, wait a minute. 2187? Well, that reminds me of 12 cubed, which is 1728. Oh, it's a shuffling of the digits. Interesting. Okay. 2 times a quarter to the n minus 1. Fine. It's just figure out the first term and then just figure out the common ratio and just keep going. So term number 1 is 2 times that to the power of 0. So it's just simply going to be 2. The second term is 2 times that to the power of 1, which is 2 times a quarter, which is 1/2. So it looks like I'm quartering it each and every single time. So the third term should be 1/16. Sorry, 1/8. But let's see. Stick in 3. So we're going to have 1 quarter to the power of 2, which is 1/16. 2 over 16 is 1/8. So indeed, that's fine. So now we know that to quarter something, you half it twice. So it's going to go 16 to the 32nd, like that. And then it's 1 over 64, 1 over 128. And now we want the 8th term. We want the 8th term. So I'm just going to work out the next few terms actually myself. Term number 6 will be 1 over 512. Then comes 1 over 2048. And then comes 1 over 8,192. Brilliant. Here, term number 1 is -2.5. Great. Term number 2 is -2.5 times 4, which is -10. Term number 3 is -2.5 times 16, which is, wait, what am I doing? You just times it by? You just times it by 4 each time, don't you? So it's just going to be -40. The common ratio is right there. I don't have to worry about this 2.5 business. Just keep on timesing it by 4. So it'll then be -160, -640. Term number 6, term number 7, term number 8. We have to get term number 8. So term number 6, 2560, -2560. Term number 7, -10,240. Term number 8, Negative 40,960? It would seem so. And I would hope so. How about here, though? How about the first 5 terms? The first term is just simply going to be negative 4. The next term, I'll multiply by 3. You see, the common ratio. So I'm going to get negative 4, negative 12, negative 36, negative 108, negative 324, and that's great. To get the 8th term, they want us to do negative 4 times 3 to the 7, which is negative 4 times 2,187, which is going to be negative 8. Negative 8,748, like that, I believe. Given the recursive formula for a geometric sequence, find the common ratio, the first 5 terms, and the explicit formula. Grand. The common ratio. The first 5 terms. And the explicit formula while you're at it. The common ratio is oh wait, we can't do that. I thought you could just pick it off. No. We're given the recursive formula, so we've got to get the explicit formula first. But the only way I'm going to be able to detect that is find the first 5 terms. So I'm just going to literally write out 2, 4, 8, 16, 32. We can clearly see that it's just the powers of 2. So we're going to write an equals 2 to the power of n. And then to find the common ratio, which is r, we're just going to say 2. And yeah, that fulfills all the requirements. Great. Next one, negative 3. Times that by negative 3, will you? Fine. 9. Oh, wonderful. Great. Great. R is negative 3. And the nth power is negative 3 to the power of n. Oh, sorry, the nth term is negative 3 all to the n. Here, wait just a second. Oh, that actually is fine. Okay, so we begin with 2, and then we keep on multiplying it by 5. So it's going to go 2, 10, 50, 250, 1,250, just there like that. The common ratio is 5. The nth term is going to be, well, okay, so I know my powers pretty well. It's going to be the nth power of 5, and then you do something to it. But what do you do to the nth power of 5? So there's an actual formal technique to figure this out, but in my case, I'm just going to multiply by 2/5, and that's fine. As for here, the first 5 terms, so term 1 is negative 3. Term 2 shall be negative 9. The common ratio is 3. The nth term is the negative of 3 to the n. Just there like that. And let's move on now. Given the first term and the common ratio of a geometric sequence, find the first 5 terms and the explicit formula. Great. So the common ratio of a geometric, the first 5 terms rather, 0.8, then comes -4, then comes 20, then -100, then comes 500. So the explicit, the common ratio is obviously -5. They already say that. But anyway, the explicit formula, well, that would be an equals. You have to do something to the nth power of -5. Well, what we're going to do is we're going to take away 1 and then times it by 0.8. How about that? That seems to work just fine. So the first 5 terms of this one will be 1, 2, 4, 8, 16. So it's the n-1 power of 2. Did I say un when this should be an? It doesn't really matter. Whatever the convention is. Plus, I can always do this to create an an. How nice. Given the first term in the common ratio of a geometric sequence, find the recursive formula and the 3 terms in the sequence after the last one given. And the first and the 3 terms in the sequence after the last one given. Don't know what you're saying. I'm going to work out term number 4. So -4, -24, -144, -864. Why not? And the nth term will be 6 to the power of n, and that has to be minus, and then you have to do 2/3 of that, or 4 out of 6, I guess is a way to think about it. There, right, term 1 is 4, common ratio is 6, so it's going to go 4. This is really just the negative. So it'll be 2/3 of 6 to the n, but we should check that. So what is 2/3 of 216? Well, you divide 216 by 3 and you get 72. Times it by 2 and you get 144, so that seems to work. Right. Next comes this one. So it goes 2, then multiplied by 6 and you get 12. Times that by 6 and you get 72. Times it by 6 again and you get 432. Times that by 6 and you get 2596, like that. That's good enough for me. So what's the nth term? Well, the nth term is a modification of 6, or the nth power of 6. So you just put 2 over 6 just there like that. And that's really 1 over 3, isn't it? So that's all fine. And now for this one here, it begins -4, and we keep on quadrupling it, times it by 4 over and over again. So we're going to get -4, -60, -64, -256, and -1024. And the nth power, well, that would be some modification of the nth power of 4. So we can just write 4 to the n. We can stick a negative sign in front of it, and that seems to be sufficient. That's absolutely fine. Given a term in a geometric sequence and the common ratio, find the first 5 terms, the explicit formula, and the recursive formula. Right, so now we have like, wait a minute, please don't tell me this continues too long. Okay. It's getting a little bit hard for me personally. Personally, it's getting a little bit hard. So, term number 4 is 25. Term number 4 is 25. So, blank, 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 25. The common ratio is -5. So, it will be like minus and minus there. We know the pattern by now. Then it goes 5, 1, and 0.2, because I'm just dividing by 5 to go down the sequence. And what are we supposed to find? The first 5 terms? Fine. So we're going to get the next one for them. So it's -125. But what about the explicit formula? The explicit formula. All right, you want the explicit formula? Well, it's going to be, we're going to do something to -5. We're going to raise it to the power of n. And then what are we going to do? Oh, goodness me. We're going to take away 2 from that. I think that's just literally it, isn't it? Yeah, I think that's it. Like, to get the second... yeah, that works. That's fine. That's fine. But they also asked for the recursive formula. Very well. A1 equals -0.2. And A of n add 1 is A of n times -5. There you go. Right, so the first term is 4 and the common ratio is 5. So it's going to go 4, 20, 100, 500, 2500, kind of musical. And then the explicit formula will be a modification of the nth power of 5. So 5 to the n, but what? 4/5 of 5 to the n. See the 4 of the 5. Given 2 terms in a geometric sequence. Oh, wait, we forgot to find the recursive formula. Okay. That would be A1 is 4, and AN is AN times 5. AN add 1 is AN times 5. Beg your pardon. Next up, given 2 terms in a geometric sequence, find the 8th term in the recursive formula. So term 4 is -12, term 5 is -6. So the common ratio is clearly half. So term 6 will be -3. Term 7 will be -1.5. And term 8 will be -0.75. And they want the recursive formula. So we shall tell them what A1 is. So to get A1, we're going to go back down the sequence. We actually have to double. So term 3 is going to be 24. Term 2 is going to be, term 3 is going to be -24. Term 2 is going to be -48. Term 1 is going to be -96. Great. And what you do to get from one term to the next is you just multiply by a half. That's it. Here, the 5th term is 768 and the second term is 12. So gap 12, gap for term 3, gap for term 4, 768 for term 5. And guess what? and multiplied by r there and there and there again. So how can we find the common ratio? Well, it appears that 12r cubed is equal to 768. So let's do 768 divided by 12. And when we do that, we're going to get so 12 times 50 is 600. So it's going to be I think it's just 63. I think it's 63. Yes, it's 63. I'm pretty sure of it. Is it really 63? It's embarrassing that I have to check this, but tiredness creeps up on us all. No, it's 64. Goodness me, 60. The cube, of course, the cube number. So R is 4. No problem. No problem. So, working out the rest of the sequence now. 3 there. 48 there. Then it comes 96. Then comes 192. Right. So we've got term 5. Term 6. We're going to have to multiply that by 4. I can do it. 3072. How about that? Term 7. 12288. Term 8. 49152. How about that? The recursive formula, huh? Okay. A1 is 3. And to get to the next term, you have to multiply the prior term. So we're going to write A and add 1. You have to multiply the prior term by 4. And there you go. Now, term 1 is negative 2. Term 5 is negative 512. Goodness me. How do I proceed? So here it's by R. 4 times. So what do we do? So we write down negative 2, R to the 4 equals negative 512. And so we're going to get R to the 4 equals 256, dividing both sides by negative 2. So R to the 4 equals 256. So R is 4. So now to get the rest of the sequence. So we have negative 8. Negative 8, negative 32. Negative 128, and that is fine. But they want term 8. So I've got to multiply this by 4. Wait. Am I sure? What if R is negative 2? So I get minus plus minus plus minus. It could be. It could be. I don't know. Okay, but I'm just going to assume that it's 2, that it's 4 just for now. Okay? So Great. The recursive formula now, well, that would just simply be that a1 is -2 as given. And n add 1, well, that would be 4 times an, right? Okay, last one, and then I have to take a little bit of a break. So 3,888, 108. So 108 times r squared equals 3,888. And can you divide that now by 108? Okay, so 108 times by 30 is 3,240, and that leaves a gap of 648, and 648 is 6 lots of 108, so it's 36, so the square root of that is 6, so the common ratio is 6. So we can now get the intermediate terms. First, divide 108 by 6, so we have 18. And then by 6 again, so we have 3. And then times it by 6, so we have 672. Wrong. Times it by 6 properly, 648. But we want the 8th term, don't we? All right, so we need term 5. So that would be for the 6th term 22328, and for the 7th term 139968. Now for the 8th term, I'm just gonna do 140,000 times by 6 to get 840,000, and then I'm going to take away 32 times 6, which is like 196. So 840,000 take away 196, that would be 839,804, something like that. Now for the recurrence relation, or the recursive formula, however you want to term it, a1 is simply 3, and to get the next term in the sequence, you do the prior term multiplied by 6, just there like that. Okay, so tiredness affects us all, so I must take a quick break. I must take a break. And yeah, maybe I'll be back later. Be well.